Okay. Determine the inverse function for that. So what are the two steps I have to do to write the inverse function? The function. How do you get the inverse? Two things, always. And you can actually do them in either order, but I recommend you always do them in the same order.
You flip it in negative?
You switch the variables and solve for y. That's it. Switch the variables, and I like to do that as the first step. Now, solve for y, and of course that's the difficult part. Solve that for y. What's the next step?
So you want to get y out of the bottom.
Yeah, you wanna solve for y. So what's the first step for solving for y?
And multiply by the...
Okay. So it's 3 minus 2y times x equals 5y. That's the first step. Second step?
Then divide by y.
No, let's distribute. In other words, we've gotten rid of the denominator. Now let's get rid of the parentheses. So multiply the x by what's in the parentheses gives you 3x minus 2xy equals 5y. Now this is the key step right here. What do you do now? If I'm trying to solve for y,
divide by y.
actually not. What you want to do is you want to get every term that has a y on it on the same side of the equation. Everything else on the other side. So I'm going to add 2xy, okay, which gives me this. And that's okay. I got every term that has y on it on one side of the equation. Now, what can I do? Now this is another step that you kind of have to think about. Factor out the y. Okay, with me?
Yeah.
Now I can solve for y. What do I do last?
Then you can divide by
Exactly.
5 plus 2x.
And there's your inverse function. And it's hard to get these without going through that whole process. In other words, there's the function we started off with, and the inverse function looks something like it, but not quite. But that's all you do, is you switch the variables and then solve for y. And the algebra is a little tricky, but not that tricky. All right. Let's go to the next one. I've actually seen these problems before this week. Let me blow it up. Oh, I hate Windows 10, I tell you. All right, number 2. Which of the following equations matches the graph? What's the parent graph look like? That's the greatest integer function, right?
Yeah.
Parent graph looks like this. In other words, the open circle is to the right of the line. Okay? And that's filled in, that's filled in. And of course, it goes the rest of the way the same way. Okay? So the first thing I can tell, and greatest integer graphs are a little tricky because vertical and horizontal shifts look the same. In other words, if I take my parent function here and I shift it horizontally, it's going to look exactly the same as if I shift it vertically by that same amount. So it's a little tricky figuring them out. If I look at that graph though, I can tell that each line is no longer has a length of 1, but it has a length of 2, right?
Mm-hmm.
So what happened to the greatest integer function? It got multiplied by some factor, and it was a half. In other words, if I start with my greatest integer function like this, and I said, well, what would this look like? That is a horizontal expansion factor by a factor of 2. Right? And that's what we're looking at in that graph. Each line is 2 units long instead of 1. So my greatest integer function has been expanded. So I'm definitely looking for that half inside the function. And I see it in a couple places. I don't see it in B or E. I see it in A, C, or D. So that's one of our functions. Also, looks like it's been shifted down by 3 units, right? In other words, from the greatest integer function, this appears that this line right here is sitting 3 units below where I've graphed the basic parent function. So it looks like there's a shift down of 3. But there's more going on here. In other words, my greatest integer function is a staircase going up, whereas this graph is a staircase going down. So if a reflection has happened, over which axis has it happened?
The y-axis.
No, if you reflected this graph that I've drawn here over the y-axis, then the open part of each line would go to the left. In other words, it would look like this, right?
The x-axis.
So it has to be a flip over the x-axis. And that flip would cause these stairs to go down just like we see in this graph. Okay, so we know we need a negative sign not inside the greatest integer function, but in front. It's the negative sign in front of the function that causes it to flip, be reflected over the x-axis. Well, that's in A and D, but C's got the negative sign inside. That would be a flip over the y-axis. So it's not C. Okay? And this 3 that's inside would be a lateral shift to the left 3 units, whereas on D, it would be a vertical shift down 3 units. Well, if I did my shift first, if I did my reflection first, this line right here would stay exactly where it is, right? But this line here would go to there. And so it would look, in other words, that would just be the reflection. And that's kind of what our graph is doing, but it's also been shifted down by 3. So it looks like D. Okay? Now, there's one thing that you can do to determine whether you've done it correctly or not. And these shifts of greatest integer function are absolutely the toughest ones to deal with. They're the hardest ones to figure out. Okay?
Right.
So let's plug in a point for x and see if D is the correct answer. Plug in 0 for x. What should we get?
So...
Just not on the graph yet. Just plug it into the function. Put in 0 for x, and what do you get for y?
-3.
Okay, now let's look at the function. When x is 0, y is -3. So that verifies that we're looking at the right one. Although if I use 0, this also gives me a -3. So maybe I need to use a different number, like 2. If I use 2, then I got -1 minus 3. When x is 2, y should be 4, -4, and it is. Okay? And he is the only one that gives you -4 when you plug in x of 2. Notice A gives you a -2 answer when I plug in x of 2. Okay, so if I get it narrowed down to it's either A or D, well, plug in a value for x and see which curve this fits. Does it fit A or does it fit D? Well, it fits D. But notice I couldn't tell by plugging in 0 for x. I had to plug in a different number for x. And sometimes that's the case. When I plug in 0, I get the same value for A or D. But when I plug in 2 for x, I get a different value in A than I get in D. And the graph reflects D. Reflects this curve here.
Okay.
All right. Let's go on. We don't want to spend all of our time on that greatest integer function translations because they are tricky. How am I going to evaluate this limit? What's one of the techniques? As x goes to 3, we can almost be certain that that's going to 0 over 0, right?
Yeah.
In other words, anything else wouldn't be a hard problem, and they're not going to give it to you. But this is 0 over 0 when you just do a direct substitution. So what's the answer for solving it?
So if you use the power?
Factor everything. Factor the numerator. What's the numerator factor into?
So x minus 3 and x plus 6.
Okay. Now factor the bottom. That's difference of perfect cubes.
So x minus 3 and then x squared plus 3x minus...
This one's always plus.
Oh, okay. Second one's always plus.
Whether it's sum of cubes or difference of cubes, that last term is always plus.
Okay.
Now, that's the beauty of factoring is that I might be able to get rid of something. And now I have something that when I now do direct substitution, what do I get? I don't get 0 over 0 anymore. The limit of that is x goes to 3. Numerator is 9, so I know it's not 0 over 0. It's 9 over 27 by just direct substitution.
So it'd be 1/3.
And that is the limit. So when you have a limit like this, and your first substitution produces 0 over 0, well, know that factoring is the most likely way you're going to solve the problem. Is by factoring, cancel some of the factors that are the same, and then resubstitute. Number 4 is the same function, but they want the limit as x goes to infinity.
So then you use the
that's end behavior. Okay.
Yeah, end behavior.
Well, end behavior is based on what? Only I don't need the function. I just need the highest degree. In other words, I want the end behavior based on x squared over x cubed. Well, what is the limit of x squared over x cubed as x goes to infinity? First of all, simplify that.
1 over x.
Okay. What's 1 over x do as x goes to infinity?
So 1 over x, and x goes to infinity. Y goes to 0.
Correct. If the bottom blows up, it goes to 0. If the top blows up, it goes to infinity. Well, in this case, the bottom is what blows up. Number 5, conic sections. What type of graph would that equation be? We really don't need to do any math. We just need to look at the polynomial. It's got an x squared and a y squared in it. So we know it's not a parabola, right? A parabola would have one of those variables would not be squared. Can it be a circle?
No.
No, because the coefficients of the x squared and the y squared would have to be the same for it to be a circle. Well, so what is it?
It would be a hyperbola because they're both positive.
No, if they're both positive, it's an ellipse.
Oh, an ellipse.
In other words, the equation of an ellipse is basically this. And the equation of a hyperbola is there's a negative sign there. In other words, if it's this, it's an ellipse. If it's a negative, then it would be a hyperbola. And the negative sign can be in front of either the x or the y. In other words, if I had the following, that's also a hyperbola. Because basically that's y squared minus x squared, right?
Right.
If it's plus and the coefficients are different, it has to be an ellipse. And there's a plus sign in front of the x squared, there's a plus sign in front of the y squared. 9 is not the same as 16, therefore it's an ellipse. Now the next question is, determine which equation it is. Well, this requires us to complete the square. And let's go through it completely. Let me write it first of all so that I can get it on my page. All right. I want to get it into the following format. I know it's an ellipse, and the full general equation for an ellipse is this. Excuse me, Dawson. I think I'm not there coughing on you. All right, so how do I make this polynomial look like this? Well, the first thing I can do is take the 1 to the other side. Okay? I know that the secret for conic sections is always to complete the square, no matter whether you're dealing with circles, parabolas, ellipses, or hyperbolas. The way I'm going to put this polynomial into this format is by completing the square. Okay? And I start that by putting parentheses around both x terms and both y terms. Now there's something I have to do before I can complete the square. What is it? You cannot complete the square if there's a coefficient in front of the x squared term that's not 1. So I got to make those coefficients 1. How do I do that?
Divide by 16.
Yeah, factor out a 16 from just these two terms. So now I have 16 times x squared minus 4x, and I'm going to leave room to complete the square. And over here, what do I need to factor out?
9.
Leaving y squared plus 6y. Leave room to complete the square, minus 1. Now, let's go inside each parentheses and complete the square. Because remember, the goal is to be able to write this like x minus 2 quantity squared, to make it look like x minus h squared. Okay, so in order to do that, how do I complete the square on the x part?
Leave one another.
Take half of that coefficient and square it. That's all it is.
Yeah, so plus 4.
Okay, now, at this point, I have not changed anything. What I've written down at the bottom right here is exactly what I started with. You can check it, and that's not a bad thing to do at each stage of completing the square, is make sure you haven't changed anything. I'm looking at exactly what I started with, okay? So now you told me to add 4 right there. Well, how much did I just add to the left side of the equation? When I wrote a 4 in there, how much did I add?
64.
So I got to add 64 to the right side to balance it out. Now complete the square on the y term.
Plus 9.
And how much did I add again to the left side?
81.
So I got to add 81 to the right. Okay. Now simplify everything. I can write this. You can always, once you've completed the square, you can always write it as a linear term squared, like that. That's the whole reason we complete the square, is so that we can write it as a linear term. What's this linear term going to be?
Y plus 3 squared.
And it's all equal to 144 after I add those 3 numbers together. Okay? With me?
Yeah.
Now what? Now I'm not quite there. I got the x minus h and the y minus k, but I need a 1 on the right side. How do I get a 1 on the right side?
Divide by 144.
Yeah. So when I divide by 144, now I'm going to produce my a and b squared underneath, which is where I want them. Well, 16, I can divide top and bottom by 16, and this turns into x minus 2 quantity squared divided by 9. You see that?
Mm-hmm.
This one turns into y plus 3 quantity squared divided by 16. And it's all equal to 1. Now I have it in perfect format. Okay, so if I wanted to graph it, I know where to start. Where's the center of this ellipse?
It's at 2 minus 3.
Correct. What's A and what's B? Is it a vertical ellipse or a horizontal ellipse?
It's a horizontal.
Actually vertical.
Vertical.
The reason it's vertical is because the biggest number is under the Y.
Right.
And the biggest number is A, always, or A squared. In other words, 16 would be A squared. So A is going to be 4, and B is going to be 3. Okay, there's the center of the ellipse. I know it's a vertical ellipse, so I can draw it. And I know this distance is 4, because that's A, and that short radius is 3. And there's my ellipse. But most importantly, I took the raw polynomial and converted it to the standard format for an ellipse. And that's what you always are going to do, no matter whether you're looking at an ellipse, hyperbola, parabola, doesn't matter. Whatever polynomial they give you, to convert it, you're going to complete the square, always. Even if it's a parabola, or circle, or hyperbola. You're still always going to complete the square. Okay, and the answer looks like B. No, sorry. The answer looks like A. All right. Determine the domain and range of that function. Write the function. F of x equals negative 2/3 square root of 3x minus 4. How am I going to figure out the domain? Remember, when you're talking domain, you want to talk about what can x not be. It's more about what x can't be than what it can be. Well, I have a radical sign in this function, so what's the very first thing I know?
It can't be negative in the radical.
What's inside the radical cannot be negative. And so the way I'm going to solve this is I know that 3x minus 4, that's what's inside the radical, has to be greater than or equal to 0. And no matter how complex this is, you can always solve it by doing this. Just take whatever's inside the radical and force it to be greater than or equal to 0, and then solve that inequality. What do you get when you solve this?
X equals 4/3.
X is greater than 4/3?
Greater than 4/3.
Okay. So if I look down at my answer, that domain for A works, right? 4/3 to infinity in interval notation. Unfortunately, they've got that answer for every single thing almost. No, they don't really. In other words, it's either A, B, or C, right? Because the domain goes from 4/3 to infinity. There is a slight difference also. It says greater than or equal. So it's not B, because B has a parenthesis next to the 4/3. So now we're down to either A or D, or C rather. Yeah, A or C has the right domain. And it's the same domain. Now let's talk about range. The range is what f of x can be. This one you have to think about a little bit. Let's say that I said this. If this was the function, what's the range limitations? Can f of x be negative?
No.
No, it'd have to be positive, right? In other words, if I say y equals square root of x, then y has to be positive also, or 0. So immediately, when you have that radical sign, you're affecting what the y is going to be equal to. Well, if this thing has to be greater than or equal to 0, and I'm multiplying it by minus 2/3, what does y have to be? Positive or negative?
Negative.
Correct. And it can be anywhere from negative infinity to 0. There's no way f of x can be positive because this has to be positive, and I'm multiplying this positive by a negative 2/3. So f of x is always going to be negative. And if I make x big enough, it can be negative infinity. So I know the range goes from negative infinity to 0 with a bracket, because it can be 0. If x were exactly 4/3, then f of x would be 0. But that's as big as it can get. Okay? So now we're looking at answer C. Answer C is the only one that has the proper domain, and it has a range that goes from negative infinity to 0, with a bracket about the 0. Okay? There's a really good limit problem, but I think it's on the other side of this page. Is there a backside to this page?
Yeah, I can send it to you.
Okay, or just read me the one that's got square root of x squared plus 5. Do you have this kind of problem on there?
And it's in a limit?
Yeah, and it's the limit of this thing as x goes to 3. Notice that as x goes to 3, no, that wouldn't work. We need this to be, well, I might be remembering it wrong. Why don't you go ahead and take a picture of it and send it to me. I was trying to save a little time, but
okay.
Should be quicker this time, because as soon as you go to share that picture and type DA, it should bring up my entire email address.
I'm looking for see what page it's on. Do you know if it would be a calculator problem or a...
I do not know. I'm not even positive it's part of this material, but it's really a great limit problem, one that I've never seen before, where after you do the first factoring or your first step, you still get 0 over 0. And you got to do another thing to it. But I can't remember precisely what the problem was. But we don't need to do that problem. Go ahead and take a picture of whatever page you want and send it to me, and we'll finish our session out on whatever problems you send me.
Okay.
Tell me when you've sent it so I'll know when to look.
I just sent it.
What's that?
I just sent it.
Okay. This up a little bit. Let's see if I can find the problem. I don't see it on here. No. I might be thinking of something else. Well, yeah, we'll just start at the top here. So, which sigma notation represents that series?
So starts at I equals 1, and top should be 32, and then 4i plus 1, so b.
Correct. And is all you really have to do is check to make sure the first term and the last term is correct, right? In other words, the first term has got to be 5 in b, and the last term has got to be 4 times 32 plus 1. Well, 4 times 32 is 128 plus 1 would give you 129. So we know that it has to be that one. Although there's never a unique answer, I should add that this series could actually be created by a number of different sigma notations. Okay, but none of these ones that we're looking at will create that series except B.
Right.
All right. So number 9, good old problem that I didn't know how to do until my first session with you. We have a point that satisfies the function f of x. Well, what happens to that point if I take f of x and translate it by doing minus 2 f of x over 2 plus 1? In other words, this is g of x. So, first thing, let's figure out which of these translations affect which coordinate. The minus 2, does that affect x or y?
Y.
Correct. Only the y, right?
Yeah.
Okay, so how does it affect it? And we're going to do that one first. Always do your reflections first.
It flips it over x-axis, and yeah, the vertical stretch.
Vertical stretch by a factor of 2, and they flip, so the 1 becomes what? Just based on this.
The 1 becomes -2.
Correct. What other translation affects the y value?
+1.
Okay, and that's the only thing. So we know our new y value is that, right? I went from minus 2, added 1 to it. I'm now at minus 1.
You're right.
What affects the x value?
The x over 2.
The 1/2 that's in front of the x. Make sure you realize that that's the same as f of 1/2 x. And what's the consequence of that 1/2 on the x coordinate?
So it'd be 3 over 2.
No. Remember that if I have a coefficient in front of my x, it's not a stretch factor. I mean, it's a stretch factor if it's between 0 and 1. It's a shrink factor if it's greater than 1. In other words, it goes the opposite of that coefficient. When I have a coefficient in front of the function, if it's greater than 1, it's a stretch. If it's between 0 and 1, it's a shrink. But when I have the coefficient in front of the x, not in front of the function, it's the opposite. In other words, 1/2 is going to expand it by a factor of 2, making the 3 a 6.
Oh, okay.
And that's the answer, 6 comma minus 1. If this was a 3, like that, then it would shrink it by a factor of 3, and this 3 would turn into a 1. You with me?
Okay. Yeah.
All right. How about that log equation? You want to go through that?
Yeah.
We have a limited amount of time and there's a lot of problems, so if you want to go through these, if you want to pick and choose, might be better.
Okay.
But this is a pretty good problem here. How am I going to solve this?
So
I got it.
you can,
Go ahead.
with subtraction, you can kind of simplify it.
Compress. What you want to do is you want to take the left side of the equation and compress it into a single log function or natural log function. So what's it going to be? What's the first step in compressing it? The whole left side of the equation.
Is it divide?
It's 3. What can I do with that 3 when I'm compressing?
I don't know.
It's the exponent. I can put it up there. Take it off of there. Okay? Now I've got two log functions that are subtracting. I got a log of this minus a log of that. When I'm subtracting log functions and I'm trying to put it into one log function, what does it become?
2x plus 1 over 2 to the third.
8. In other words, I can do 2 to the third. I can carry out that process. Okay? Now I have this. In other words, by compressing it, I've turned the left side of the equation into the natural log of something. Yeah, well, if the natural log of this thing equals the natural log of this thing, what can I say?
1.
I can say that the arguments equal one another.
Okay.
In other words, this has to be true. If the natural log of that equals the natural log of that, kind of think of it as dividing both sides by natural log, even though that's not what you're doing. You're really exponentiating both sides to e is what you're doing. But you don't even have to think of it like that. Just, it's like if it's the same natural log function, this has to be equal to that. So now we just have to solve this. And that's relatively easy to solve. Let's go ahead and do it though, just so I can point out one other thing about when you're solving log equations. So go ahead and solve it. What do I do first?
So you want to get the x by itself.
Okay, what's the first step?
Multiply by 8.
Okay, that makes 8x minus 8. I'll get rid of that. Now what?
Then you can subtract, subtract the 8 and then
subtract 2x from the right side. So now I have x equal 3/2. Now, let's just make sure, and because with log equations, you frequently end up with two answers, and one of them is going to violate the domain. Okay? Well, in this case, we only ended up with one answer. So, does 3/2 violate any domain? And in order to check, you have to go back to the original function. You can't take, in other words, I can't check this step here. I got to go back to the original function. In fact, I got to make sure that 3 is in front. That's the original function. Well, does an x of 3/2 violate any domain?
No.
No, because the domain restriction is the argument has to be greater than 0. Okay? Well, that's greater than 0 with an x of 3/2, and so is this. But say I would have come up with an x equal 1. Well, that violates that domain right there. You cannot take the log of 0. You can only take logs of positive numbers. If I would have come up with an x of 1, there would have been no solution to this, because I absolutely cannot violate the domain. 3/2 was fine. So 3/2 is a proper solution. If you plug in 3/2 in here, you would find that that equation is still an equation. All right. And that was answer A. All right, 11, pretty straightforward. We're looking at hyperbolas. Is this function a vertical or a horizontal hyperbola? And why?
It would be vertical because the A is
horizontal if the negative is in front of the y, vertical if the negative is in front of the x.
Oh, because it's, okay.
Okay. In other words, as long as I have x squared minus y squared, that's going to be a horizontal hyperbola.
Okay.
If I've got y squared minus x squared, that's going to be a vertical hyperbola. Well,
right,
clearly I have x minus y squared, so it's definitely horizontal. And where's its vertex? Where's the center?
Is that, what, -4, -1?
Correct. Which one of those horizontal hyperbolas has a center at -4, -1?
They all do.
They both do, don't they? Okay, the next test is to look at the imaginary box. Remember that the way you get a hyperbola is you create that imaginary rectangle, draw the diagonals, and the sides of your hyperbola are asymptotic with the diagonals. Well, what is my A and B?
Your A is 4 and your B is 6.
Okay. So does that help pin anything down? A is the distance from the center to the vertice.
Right.
In other words, A is always measured along your major transverse axis for a hyperbola.
Okay.
Okay? Since we have a horizontal hyperbola, A is always under the x. So A is 4. And
right.
B is 6. So I need a rectangle that looks like this, where it's 4 units to there and 6 units to there. In other words, one that is wider than it is tall.
So,
well, this is hardly fair, this problem. Those two curves look identical. I don't see much difference between them. Am I missing something? Ah, yes. Ah, now I see the difference. Notice the focus.
oh, so we need to find C.
Well, yeah,
How do you?
and in fact, I think this figure, that's supposed to represent the focus. So it's clearly got to be D, right? But you're correct. Let's solve for C. What's the formula for C squared for a hyperbola?
A squared plus B squared?
Yeah, it's the same as the Pythagorean theorem. So C is the square root of 16 plus 36. C is the square root of 52. So we've got to go from there to the focus, and that needs to be square root of 52. And that's what that number is going to be. In other words, the square root of 52 is 7 and change, right?
Yeah.
Well, if you go from the center of D and you go 7 and change to get to this dot, which represents the focus.
Right.
That appears to be the only difference between this curve here and this curve here, is that this has the focus label, or has the focus in the picture, whereas this one does not.
Okay.
In terms of the curves, I think they're the same, to be honest. In other words, this formula right here fits this curve, and it also fits that curve, point for point. Those two curves are exactly the same. The only difference in these two pictures is this got a focus in it, and this does not have a focus in it.
Okay.
So that's why I would choose D. It's kind of a bad question, because A actually is a legitimate answer. There's nothing wrong with A. A is the same. A is that equation. It's just without the focus. But who says you got to have a focus in a hyperbola? In other words, the graph is just the hyperbola. The focus doesn't have anything to do with the graph. You know what I'm saying?
Yeah, yeah.
Okay. All right. It's 7:30. I guess that's as good a place to stop as any, huh?
Yeah.
All right, Dawson. Good luck on your test.
All right, thank you.
You're welcome, and have a good summer if I don't talk to you till later.
All right, you too. Thank you.
Bye-bye.